Good afternoon, everyone. It's my great pleasure to be again part of the Hack in the Box event. My name is Adam Gowdiak, and I am from Security Explorations. So that's a small security startup company from Poland. We deal with security and vulnerability research. We do different commercial and pro bono research projects. We came to life in the result of my passion to breaking security of things. And today's presentation will be about a topic which is a little bit a niche when it comes to the computer and internet security. We'll be disclosing the details of our security project SE 2011-01. That was a pro bono work that we did for a year and a half. And we think that pro bono work is an important part of our mission. We want to contribute to the field a little bit. So we want to educate you today about security risks which are associated with the less known technology and with less known ecosystems such as digital satellite TV ecosystem. We also want to show you that security in a modern digital satellite TV shouldn't be limited to the security of content, which is usually the perception of the content providers or digital satellite TV providers. So, important disclaimer, because I'll be talking about quite sensitive stuff. I want to emphasize that all the information that's provided here today is for educational purposes only. We do not promote any acts of digital satellite TV piracy. Any use of information provided in this presentation for illegal purposes is strictly prohibited. So, in case some legal actions are taken against our company, we'll of course update our web pages. So what's the motivation? So Security Explorations was started a couple of years ago, and one of our missions was to increase general awareness when it comes to security of network-connected systems. So digital satellite TV set-top boxes, the whole area of digital satellite TVs changed a little bit during the recent years because those devices started to be connected to the internet. And if you connect any device to the internet, you need to be aware of all the risks that are out there. PC users are familiar with all those risks. So that was one of our motivations. We simply wanted to find out if set-top box devices could be hacked or if there are any risks related to the malware with respect to them. Some less official motivation. So because we are quite Java freaks, this is the booting screen of a set-top box device. When we saw the Java logo out there, we just thought that let's try our skills with this. So maybe we could do something interesting. So basic data related to our project. So this was pro bono security research. We conducted the research for quite a long time. That was pretty unusual because it took us a year and a half to actually finish the project. So there were multiple security issues found, and they affected quite a bunch of vendors. So because among the vendors there were companies such as those providing web services, set-top box manufacturers, there was a semiconductor company, some condition access system provider. We treat this project as the one exposing weaknesses in the security of a digital satellite TV platform as a whole, not just in set-top boxes. So, some introduction to the digital satellite TV. Most of you probably know how this works. So basically we need a satellite TV provider which transmits a signal over the satellite to the user home installations. And what's required to receive a digital satellite TV, users usually need some kind of a device, end-device, set-top box device, and a satellite dish to receive that signal. So the digital satellite signal, the audio and video is transmitted with the use of MPEG transport streams. That's the fundamental protocol and the most fundamental specification for the whole digital satellite TV area. So what's interesting from the hacker's perspective is that, of course, there is audio and video data transmitted along those MPEG streams, but there are some specifications that also state that you can have files transmitted over the streams, you can have applications, the so-called Java applications, Java XLET. You can have also some private or operator-specific data, such as set-top box configuration, upgrades, some metadata related to push video on demand. So MPEG streams are pretty simple format. So basically, audio and video data is being encoded into some kind of packed format such as MPG2 or H.264. Same for audio data. The resulting elementary streams are split into some kind of chunks, which are called packetized elementary streams. They are large. They could be up to 64 kilobytes of data. Because these chunks are too large to be transmitted, so they are packetized again into the so-called transport stream packets, and these packets are just 188 bytes in length. They have some common 32-bit header. They have some very important field, which is called PID, the packet identifier, and this field simply denotes the kind of data that is being transmitted as a payload of the MPG stream. Of course, you can have the MPG data scrambled, encrypted, so there is also some kind of a bit flagging whether this data is scrambled or not. So that's the illustration of what I said, elementary streams. So one channel, such as, for example, HBO, can have a couple of streams. One stream for audio, one stream for video, one stream for data. Then these streams are packetized again, and we have the final stream, which is being broadcasted to the set-top box devices. And this is the transport stream. So, because set-top box devices need to know how to actually extract the audio and video data from the MPG streams, there needs to be some kind of additional information transmitted along the audio and video. So we have some special MPG tables defined in a specification which simply give information where to find a given stream for a given program. That's the first table, program association table, which has a fixed number, 0, for the PID. And we have also a program map table, and this table simply states where to find a stream for a given audio or video data for a given program. So, because today I'll be primarily talking about set-top box devices, so I need to introduce you a little bit what these things are. So these are basically the devices that have some kind of a tuner. They are connected to the television set and some kind of external source of signal. In the case of digital satellite TV, this signal comes from a digital satellite dish. So these devices turn the signal received from a satellite into content, which is then displayed on a television set. The features of modern digital satellite TV set-top boxes are, quite rich. They can allow internet connectivity. They can allow for some web browser experience. They can allow to record some programming to external or internal hard drives. So that's a basic architecture of a Java-based set-top box. I just decided to just stick to that kind of a diagram because I'll be talking about Java-based set-top boxes later. So at the very top, we have set-top box hardware. Yeah? We have some dedicated DVB chipsets which can deal in hardware with MPG streams. Then we have a top embedded OS. Sometimes this is a Linux OS or some other RTOS. We have then Java virtual machine. In case of set-top boxes, the J2ME specification states that this is usually a CDC version of Java virtual machine. Later, up in the layer, we have some kind of something that's called MHP middleware or APIs. These are the core Java APIs which allow to deal with the set-top box hardware, which actually provide the functionality of a set-top box for Java developers. And at the very top, we got the main set-top box application, which makes use of the middleware and API which are below. So those core APIs which I mentioned, Multimedia Home Platform, MHP, they are defined in a specification which can be downloaded from a website, and they provide basically that functionality as mentioned here, some low-level MPG access, some media control and playback, application lifecycle. This is with respect to Java applications, some graphic user interface, and of course, security. So Java XLab, that's a very interesting thing because normally users are not aware that these things could be executed in a set-top box. So Java applications in the set-top box environment are called XLET, and they are broadcasted by the digital satellite TV operators inside MPG streams. So there is a special AIT MPG section which defines the different attributes and characteristics of a Java application to be executed on a set-top box. So digital satellite providers have this kind of power to execute applications on set-top boxes. This is a concept very similar to Java applets, which means that XLETs are executed in a sandbox, security sandbox, so that there is no harm to the environment they are executed. And what's also important, I don't know what happened. Okay, what's also important is that, well, the eclipses are usually bound to the given programming. For example, if there is an HBO broadcasts some kind of application, so that application, the lifetime of that application is during the time a given service is selected, or which simply means that for the time a given user watches a given channel. I apologize for, I don't know what happened. Okay, I'll try something else. I am changing the resolution, so maybe it's going to work. So. An idea what went wrong? Okay, so maybe I'll just proceed without a couple of slides, because, you know, I got plenty of them. And well, okay, I was talking about the Java Xlet, so we don't have quite a picture on this slide. So I mentioned that they are bound to a given programming, and what's interesting is that they could be also installed by a digital satellite TV operator on a set-top box system. They could be installed in a persistent way. They could auto-start in some way. So there's no slide, but I can still talk about it. So yeah. The next slide simply is about the actual target environment we worked with. I mean, so I see the guys with flashlights, so something serious happening over there. So all of the tests when it comes to this research of the digital satellite TV, it was conducted in a real-life digital satellite TV environment. So we work with one of the biggest providers in Poland, and which has about 820,000 subscribers, 30 plus HDTV channels. So we worked with the set-top box devices of Advanced Digital Broadcast Company. Oh, yeah, something. Yeah, thank you. So that wasn't my fault, I guess. Okay, so we work with the set-top box devices of Advanced Digital Broadcast Company, one of the biggest players in the set-top box manufacturing market. We work with the devices which were based on ST microelectronics chipsets that were using the CONLAX conditional access system with chipset pairing for content security. There are also some kind of limited set of trusted internet services, because the devices we worked with, they were connected to the internet, and the digital satellite TV provider made the environment more rich for the users of these devices, so they could use some services for richer experience. And the next slide shows this. So here we got that kind of architecture of our target environment. We got the users, set-top box devices, we got the internet, the infrastructure of the digital satellite TV provider with just a couple of trusted services. Everything here goes through the SSL connections. We got some photo gallery services as well. So these are the set-top boxes we worked with, and these are the actually not, I mean, they are all based on ST microelectronics chipsets. There is also one more box we didn't work with respect to this digital satellite TV provider, but for the scope of this research, it doesn't probably matter much. So the set-top boxes were running two different kinds of software. We had the Hermes and Carbo software. They are pretty much similar when it comes to the MHP middleware and the Java API middleware. The actual important thing about the other software, the Carbo one, the newer one, is that it had much more modular architecture. It was using more dynamic link libraries, so it was a little bit easier to analyze it. So set-top box hardware, just for the record, the ST microelectronic system on chips, which means these are dedicated microprocessors with a couple of cores inside, separate cores. Each of the core was doing something else. So we had a core which was, for example, running the main Linux OS distribution. We had also some cores which were simply doing the MPG decoding of audio and video. We had also some cores which were using the DMA transfer or cryptographic operations. So, of course, we got the situation and the environment where security of content is important. So digital satellite TV provider and set-top box manufacturer doesn't want anything to happen to the set-top boxes. They don't want them to be hacked. So they did something to create secure environment of these set-top box devices. These are some of the features they had. So first of all, there was no other way to connect from the set-top box devices with any other website than the trusted one. Only HTTPS scheme could be used. There was also some restriction with respect to the certificate of the target web server. The set-top box was only able to connect with a trusted certificate web server. So there was, on some set-top boxes, we had a change root sandbox environment. We of course had the unprivileged user ID. We had IP tables, some kind of filtering, no listening TCP ports, encryption when it comes to the flash, something which was really pesky from our point of view. One big image when it comes to the statically linked image for the set-top box main application. It was, of course, more difficult to reverse engineer such an image. There were custom Java file systems, which were only visible from the Java layer. They were not visible from the OS layer. We had custom JVM security manager, no way to execute shell from Java. There was no unsafe class. This is the class which allows to read and write process memory. It was removed from that distribution. And finally, there was a code, Java code, which was being obfuscated for the main set-top box application. So, well, that's the state we sort of found out when it comes to the initial state we started this research with. So, and we of course wanted to get access to the device. So we are pretty lucky because we found some kind of cross-site scripting vulnerability in one of the trusted web services. This of course shouldn't happen, but it did. So the vulnerability was pretty simple. We were able to inject 50 bytes of our HTML code, which means 50 bytes of including script code, which could be executed on set-top boxes. Of course, from that point, it wasn't so easy to actually fully own the devices because 50 bytes is not enough, plus all resources that were referred from a web page on a set-top box, they couldn't come from any other protocol than the HTTPS. And as you remember, HTTPS was also guarded with trusted web server certificates. So it was quite impossible for us to go into that direction. So we used another vulnerability. Another vulnerability was in the photo gallery service as well, but we found out that it simply allowed it provided some extra functionality related to the album list. Users could simply add some albums, some photo albums that they were watching through set-top boxes to some kind of favorite albums list. And this is a sample of the web page as visible from the set-top box, and you can see the exact place where 50 bytes of user-provided code could be linked. And that was a key finding because later we've also found that these album names could be added, more of them could be added to one web page, which means that we could chain in some way our code on one web page. Yeah? So an MHP specification state that from JavaScript, arbitrary packages, classes, and methods, Java methods, are visible with the use of some special object called packages. What does it mean? It simply means that we could bypass the restrictions that were at the web browser level by calling directly Java IO from JavaScript. And this is a sample page, which what this page does, it simply opens a connection from JavaScript with the use of Java in order to obtain some kind of JavaScript file. And that was a key finding because by doing this, we are able to bypass security restrictions of the web browser that were applied on a set-top box device. So we needed to work a little bit more on these vulnerabilities so that arbitrary JavaScript code execution could be gained. So what we did, we simply came up to such a solution that we use such a sequence of names for our album, photo album names. We uploaded that to the web server, and then upon parsing that web page on the set-top box, all of the code was executed, and we could actually execute any code from our local web server. Any JavaScript local file could be downloaded and executed with the use of evaluation function. Of course, some people can do everything when it comes to JavaScript. We are not Web 2.0 guys, and so we prefer Java. So we wanted to do some stuff in Java, and there is also some statement from the MHP specification which states that Java methods can be called from JavaScript with the use of those special object packages, and when they are called with the privileges of a target application. And in our case, there was something interesting because the set-top box web browser, the one which was executing our JavaScript code, was executed in a privileged context. What this means? It means that we had almost unrestricted access in a JVM environment. So we could, for example, access sensitive Java packages, and we could create our class loader objects. And this is what we did. We created a custom class loader object from JavaScript, and we defined it in a special null privileged domain in a null class loader namespace. And in order to run any Java code, after obtaining a class loader object, we simply loaded our class from our web server and executed that class, the constructor of that class. And this is the point at which we had sort of unlimited access at the Java virtual machine level, not JavaScript level, execution access to the set-top box device. Of course, using the digital satellite TV operator infrastructure and playing with the digital satellite TV operator infrastructure with their services is not very convenient, uploading some kind of, the favorite album list. This leaves track in the logs. So, we wanted to be more sure that we can continue this research and that we don't lose the most crucial bug that open access to the set-top box. So what we did after gaining access to the set-top box, we always tried to modify the web browser configuration in such a way so we enabled the HTTP scheme and we disabled the certificates verification. And this was achieved with this one line of code in the configuration file. We developed a special tool that did all of this in an automatic fashion. And actually, this allowed us for continuous, playing with the device for a year and a half, unnoticed. So, okay, so we are at the point where we have access to the set-top box. We can execute Java code. The next step is to break JVM security model, and because we had almost, like I said, almost root privileges in Java. And this was due to some kind of modified security manager implementation provided by the ADB, the set-top box manufacturer. So in this model, we have native P threads, which execute Java threads. And to each native P thread, we have assigned some kind of a PID value, the process identifier. And we have this modified application security manager from ADB. And it's interesting that it implements the different security checks in such a way so that if a given PID requesting some kind of sensitive operation, security operation, is equal to -1, no security checking is done. It was used by us later. So that was not the only interesting thing regarding the implementation of the security manager, because we also found out that the actual permissions granting object, the object that we're granting root permissions to different Java threads and processes, could be simply obtained, the reference to that object could be obtained, and API functionality of that object could be called. So first we obtain the instance of the object, and then we simply called grant root permission to a given target PID. So this was not guarded in any way by the set-top box provider. The access to the package is defining that security manager. So for full file system access, because the security manager was blocking some access, we needed to become actually the PID -1. And we achieved that by calling one function from the SunMISC CVM class. We were attaching to the context of the -1 process. By doing this, the security manager treated us as a fully trusted Java application in a set-top box environment. So we also wanted to run in the background. Why? Because Java applications our code was being stopped at the time web browser was exciting. All the threads were being killed. So for the purpose of running into daemon mode, running in the background, we are again attaching to PID -1 to become root in Java environment, and we are creating our Java thread in the the most privileged thread group in the Java environment. By doing this, we could simply run in the background on a target set-top box. The next step in Java, usually when you gain root privileges, but you are in some environment where you want to peek deeper into the target OS. Yeah? So what you need to do, you need to bypass memory safety. What does it mean? It means that you need to read and write memory in order to see what's beneath, what kind of system is beneath. So we abuse Java Reflection API to create some kind of a type confusion condition to gain that memory read and write functionality. And that's a little diagram that shows this. So what this basically does is that we created a couple of reflection field objects, and we tricked Java virtual machine into thinking that it's accessing an object, but it was really accessing some kind of integer. So we created a type confusion vulnerability. So by doing this, we are simply able to access object's memory beyond its bounds. And this obviously means accessing the memory of the underlying process. And this is how we actually gained the read and memory write access to the target process. This is not all. Reading and writing memory is one thing, but of course, hackers usually want to execute code, native code. Can be also easily achieved. So this was done in the past for a couple of times. So we inspected JVM virtual machine structures in memory, and we modified some methods in such a way, so instead of being treated as a Java method, JVM started to treat them as a native method, which means that after executing such a method, arbitrary jump to the selected memory location could be done. So, and we used, what's also interesting here, the Java native interface specification for the seamless parameter passing. And this is how this basically looks like. So we had our method. Initially it was Java. We modified the JVM structure so it was treated as a native one. After calling a native method, that was the actual layout of the registers and arguments in the native code. So we could actually start writing code execution at the assembly level at the Hitachi SH4 processor level. So native code execution was a little bit more complex thing because we needed to write a couple of additional classes to be able to actually parse the ELF images in memory, to look up symbols to look up the GOT entry addresses. So this was done for the flexibility, for the easier development of code, proof of concept code on a target platform. So when it comes to privilege elevation at the OS level, so we are at the point where we broke JVM security, we are able to read memory, we are able to execute code, native code, the assembly level in a target set-top box system. So we can play with the target OS, and of course, because there is unprivileged user, some change root environment, we want simply to gain more privileges. And there are a couple of options with respect to this. First of all, there are a couple of leaked open and read and write mode descriptors, such as the kernel memory descriptor we could abuse. And initially we thought that this is related to the target process implementation, but later we found out that this is something bigger because this was related to the architecture of a target set-top box. Because the systems were using the Linux threads, all the descriptors open in any of the threads were shared among all the threads in a given bunch. So, and here's the kind of a change root sandbox bypass we implemented. So this is a sample of code. So, change root bypassing, it's like, hacking in 90s, but it was still possible at work, so why not to do this, yeah? We abused the leaked def key mem descriptor for doing this, and we are able to patch credentials, process credentials and capabilities in memory, in kernel memory, to become root, and then we broke the change root sandbox with that code. So that was not the only privilege elevation attack which was available on target set-top boxes. There were many more problems. There are some services which expose some file system operations over the named pies with root privileges. There were some device drivers which allowed for full kernel memory access, read and write access without no security checks. So there was also one device driver which was simply granting any capability a user requested without no security checks. So you can see the kind of security from the inside of the set-top box here. So that was not enough for us. We were root at the target system, but we wanted to become even more privileged. So we wanted kernel level IO access. Why? Because we wanted to play with the chipset, directly with the chipset's IO registers. So we wanted a more flexible way to do this. So what we did, we simply installed our kernel level system call. We used some unused system call slot number 17. We took some addresses from the proc file systems to find out the actual exact memory location where we could provide our system call handler. And by doing this, we could simply call any I/O operations from the kernel level, and those I/O operations could be used for accessing chips register space. So again, more complex things when it comes to the kernel level access. We needed to develop some more classes. These are just a few of the classes because there are in total 130 something of the classes we developed in the proof of concept code. But these are the classes that allowed us to play with the kernel symbols. We were able to actually obtain memory addresses for different kernel symbols, which was also very flexible and convenient when it comes to playing with the kernel with some device drivers and testing some things out. So now, something about how to spread malware. Yeah, I'm talking now that we got some access to the devices. Yeah, we broke Java, we broke OS, we got root, we could execute code in a kernel mode, but still we don't quite know how to automatically install malware on set-top boxes. So the key thing in that all is the Xeon web browser. That's a custom web browser that's used by the ADB and their set-top boxes. It's implemented completely in Java, and it's running as a Java TV xlet. It has some kind of extensions for URI handlers, for plugins. It has some kind of configuration settings in XML files. What's interesting is that users can overwrite these settings by writing to the flash directory. And also something that's interesting is that users can actually distinguish if they are working with a web browser or if they are working with an STB menu. That's because of the actual implementation of the web browser. So it allows for easy and website spoofing. So URI handlers. So that's the key part we abuse when it comes to executing malware in the set-top box environment. So the usual way the web browser was loading documents was through some kind of parse document method of some class. And at that point, all the restrictions regarding the HTTP scheme were taken into account. So, but we also find out that documents could be loaded with the use of the URI handlers. And when it comes to URI handlers, URI handling occurred prior to loading to any other document loading. Also, URI handling didn't take into account the restrictions from the web browser configuration. Those restrictions regarding the HTTPS protocol, which means we could abuse the URI handler to fetch data over HTTP, which was the crucial thing because we needed to fetch malware from attacker's side, not from just one of the 6 trusted services websites. So, and the URI handler that we actually abused, this was the AIT handler. this is the handler which is invoked for an URL like that. You need a .ait postfix in the URL. And the implementation of this URL handler retrieves files from the so-called interaction channel. So what's retrieved is the so-called AIT file. And that file simply specifies the Java exit application which should be invoked on a target set-top box. And that's more or less the format of the AIT file. It's in a text, but normally it's in a binary format. It can be found in MHP specification. So we could say that, we want to execute DVB Java application, we want this application not to be visible, we want this application to auto-start, and we want this application to be fetched from that HTTP protocol with the use of HTTP over this interactive channel. And there were some problems, because by default, the set-top box environment didn't allow for unsigned eklets to be executed. So there were some environment settings which specify that only signed eklets could be executed. And there were some security checks for that. But there were problems also at the class loader level. So because the JVM configuration allowed for the root class path and the whole environment, we could abuse this. And by calling some arbitrary class from some package 1, package 2, with some class name, we could fetch arbitrary files from some kind of from a local file system. Yeah, we also could abuse the loading order of the classes in the system, because we could load and launch xlets prior to any security checking. So what we just needed, we needed our xlet to appear in some local path, in a local file system. We didn't know how to achieve it, but we found a way for it. So, and the way to achieve it was through the interactive challenge file systems. Think of it about some kind of the NFS-like file system tunnels through HTTP, which is automatically mounted at some mount point in a set-top box device. In our case, this was the mount point, OCHT and some number directory. So at the time of parsing the AIT file, the URA handler simply first mounted our to-be-executed xlet code at that directory. And since at that point we had some files, Java class files, available and visible from the local file system, we could abuse the way class loading simply proceeded in a set-top box. So we defined our xlet in such a package. And this resulted in loading of the xlet from the mounted file path, and this was from acquiring the bytes of the xlet from our web server. And finally, what's the most important, this was done prior to any security checks, prior to any signature checks. So what we did, we developed automatic tool for doing all of that xlet execution and AIT file preparation. We tested that stuff on all of the decoders we had in our lab, and it worked. So, which means that we could conduct the malware spreading scenario, and basically could proceed as following. First, user visits, in step 1, user visits a photo gallery service, and then there is a specially crafted web page with the injected 50 bytes of JavaScript code. That JavaScript code is downloaded to the set-top box, and that JavaScript code opens AIT file. AIT file is again downloaded to the set-top box, processed by the set-top box, and set-top box parses the AIT file and fetches the xlet and executes the xlet prior to any security checks and prior to any signature checks. And that's actually the malware spreading vector we found out. And by doing this, we proved that it's possible to put malware into the set-top boxes just by having a user visiting one of the trusted web services. Okay, now details regarding the backdoor installation case. Usually malware wants to be persistently installed in the system. We again abused the way the web browser was launched, and the web browser parsed the configuration file. We simply imitated some kind of a script engine. We added one line to the browser configuration, and we simply left our class in the Flash directory. So having a class in the Flash descriptor, in a Flash directory, we are able to load that class upon the web browser startup. So every time the set-top box was starting, the web browser was starting. Every time web browser was starting, the configuration file was parsed, and our Java code was executed. And all the steps regarding privilege elevation, going into daemon mode, could be done, and the whole execution could proceed completely unnoticed for the user. It was not the only problem when it comes to set-top boxes. There were some problems regarding the communication XLET. That was the XLET that was used by the digital satellite TV provider to establish some kind of a communication channel with target set-top boxes from its own infrastructure. And we found a way to abuse the XML parser of that XLET. And we could achieve some kind of authorization bypass. We are able to spoof our messages sent over the Jabber-like XML protocol, so that the set-top box and the infrastructure at the operator side thought that these messages were coming from the operator, not from arbitrary user. So our messages could reach target set-top boxes and could be processed by set-top boxes. What this means, for example, we could delete recordings on the set-top boxes, or we could spawn some set-top boxes, some pop-up messages, some email messages on a user screen, which wasn't maybe very interesting, but still some kind of an issue. This one is pretty interesting. As I mentioned in the beginning, MPG streams transmitted along the audio and video streams could contain private information. So in the case of our target infrastructure we worked with, there were some private streams which were carrying the invoicing data. We found out that this data was simply zipped data, so it wasn't encrypted, and actually we were able to verify that in December 2011, that's an error. In December last year, we were able to receive about 820,000 invoices for the users of the digital satellite TV service. So that's rather sensitive business information when it comes to the amount of money people pay every month to the subscriber, what kind of promotions they choose, because this was the stuff which was visible from the invoicing, because there was information about what kind of promotion a user sign up when it comes to signing up to the given service. Some other interesting thing, we find out that the software update service was broadcasted to the set-top boxes in encrypted form, which is good, but the key to that software upgrade service was broadcasted in plain text. So everyone could get access to that key. So the encryption doesn't probably make much sense in that context. So some other thing, because we are also working with some devices which allowed for arbitrary access to the push video on demand service. We played a little bit with the CONAX entitlements and with the CONAX conditional access system. We implemented quite comprehensive and advanced smart card I/O instrumentation in Java. So we were able to simply watch messages, exchange with the set-top box and smart card. We could intercept them, we could change them, we could actually do anything on that link. So, and we find out something interesting. So the problem was the following. At the time of renting a given movie, which was supposed to be just 48 hours, the operator was sending the entitlements, which are the access rights, to the set-top box, which were denoting the whole calendar month. Yeah, like from the 1st to the 30th, or from the 1st to the 31st. Yeah, 31, yeah. So this was, of course, vulnerable to the easy replay attacks. We could simply sniff for a given message. We could pin down the exact message which was giving the access right to the smart card. After 2 days, operator was sending another message which was disabling access to a given movie. But what we could do, we could again inject the message in the form of the ISO ISO 7816 APDU to the smart card, and at that moment we could enable again the entitlements to watch the movie, just because the period was the whole month. And that wasn't the only issue we found. The other issue was even more interesting. We found out that at some point of time, we rented some movies in November. Oh, again, I got 2012. So this was 2011. We rented some movies. So in December, the card was showing the following access right. No access right for December, but still valid access right for November. So what we found out that at the end of December, by simply replaying the access rights, the entitlement messages to the card, we were able to enable the access right, but what's more, the card was releasing the keys and we were able to watch the movies. So our initial hint was that there could be some kind of the bitwise OR mask between those entitlements. We are not sure. This wasn't confirmed by Conax, but definitely this was an issue that shouldn't happen. Okay, remaining issues. There are lots of them. I just go fast through this. So brute forcing against some services. 4 pins to gain access to the user account without no locking mechanism. That shouldn't happen. Some reconfiguration issues regarding the environment variables. No password for root account, which wasn't an issue from the beginning, but at the time of enabling a telnet service, this was an issue. Some capabilities in the process space, some kernel I/O access without the need for the root account. Oh, that issue is some interesting. We had insecure network infrastructure. We found out that ADB company, I think, well, we think that this was the ADB company's developers were using and working in a real-life infrastructure. So, because we found out some developers portal, we were able to access some kind of web pages of some not released software, some test software. This shouldn't happen. There was no firewalling, no address checking, no credentials checking for that, and it was like having a developer's infrastructure being exposed to the outside world. Okay. That was a lot of bugs and a good amount of work when it comes to reverse engineering everything in order to find those bugs. So how it all started and why was this possible? So unfortunately, I need to say that this usually happens in the same way. So simply because there is too much information left in binaries. So when it comes to embedded devices, there are strings, paths, messages, some debugging assertions, and they, of course, allow to get some clues on what a given piece of code does and stuff like that. So there are some text files we could retrieve some information from, like configuration file for the web browser, some information about some other XLET started in the environment of the set-top box. And what's also important, there are lots of debug interfaces left in set-top boxes. There are some debug console shells. There are some hidden screens. So we could enable those hidden screens by simply entering a special sequence of commands from the TV remote. These probably are not going to work at the moment because these are the ones that work in the past, and every time new software upgrade is applied, these codes are being changed. But anyway, we were able to display additional menu on a TV screen, a developer's menu, some kind of debug menu, and we could retrieve some kind of extra information about the set-top box operation and implementation. So, well, that wasn't enough. Of course, we did some extra work. We went some extra mile. So we did some runtime API tracing. What this means, we had a way to execute code at the native layer. So we built some kind of runtime API tracing infrastructure. We were able to simply trace arbitrary libc calls, IOCTL calls. This was very important because we could find a lot about the device driver's operation. Here's a sample of our runtime tracer, and we use the IOCTL tracing at the library libc level to find out what kind of arguments are used to the IOCTLs of a given device driver. So we also did a lot of MPG sniffing because, as I said, there are many private sections, and private sections are usually, carry some interesting stuff like, software upgrades or some conditional access information or some private data like billing information. And sniffing MPG data from Java was quite simple because we could simply make use of the API, the MHP API or some other API, all in Java. So what we also did, we love to build tools to make our research, progress, to make it move forward. So we also built some kind of SH4 processor code emulator. We did this for the purpose of decrypting the bootloader image. So it was like, we emulated the SH4 code on a PC. We proxied all accesses to the crypto processor over the internet and obtained the results in our emulator. By doing this, we are able to decrypt the bootloader code, which used chip-specific key. We didn't have access to that key. This is why we needed to proxy all the operations to the chip. So finally, what we did, we extracted CVM classes. We used the CDS class file format. We wrote some static analysis so that it worked in most cases. These are some numbers which show, how many classes we are able to extract from the MHP middleware. And why we actually tried this? Because there was some kind of inconsistency. The obfuscation of the Java classes for the main MHP application was done. But when it comes to the core JVM classes and the fundamental MHP middleware, this wasn't done. So we could actually obtain the source code by decompiling of these Java classes and then analyze it for some other weaknesses. Oh, that's a sample. It's been done 2 weeks ago. I mean, the sample of just the addresses from the binary when it comes to some classes available from one of the devices. Proof of concept code. Well, as I said, it was pretty comprehensive. 34,000 lines of source code that's in Java. Yeah, I know. It's probably not happening every day, but, well, we tried to figure out, what kind of activity, malicious or software could potentially do on a target system. So we implemented over 70 commands. Our code worked on all those devices we had in our lab. It was compatible with similar but two different processors. It illustrated all of the attacks we discovered. The code simply illustrated privilege elevation, malware installation, access to all sorts of information. There is not much time today to present the proof of concept code because I would need probably one separate presentation for this. Some extra information is available on our website with respect to this. So what's interesting is that because security of content is important for the set-top box manufacturers and digital satellite TV providers. What we did at some point of time, we decided to find out if it's possible to capture HD premium programming, and it turned out to be possible. It requires some amount of extra reverse engineering because there was no known Linux DVB API. We needed to actually dig a little bit further into the kernel buffers. We needed to track some pointers in kernel buffers, but we did this, and we are actually able to dump over the network from a set-top box arbitrary MPG streams. And I don't know if I have time to show you just a demonstration. 6 minutes, that's a good one. So I don't know if I can because we have some kind of software here. Okay, so we did the capturing, and when it comes to the capturing, these were pure, this is HD capture. So maybe some funny, yeah. Animal Planet HD, and as you can see, it's like, no disruption in the image, and it can actually be viewed, no problem with the capture. So we tried that on different decoders, and it worked. So, well, so we had some kind of, reservation whether it's going to work, how much of data is going to need when it comes to sending over the network, but it worked in our LAN network. We could simply extract the MPG streams of HD data and dump it straight to the file. This is the file that was straight dumped from our set-top box. Okay, coming back to the presentation. Yeah, so what we did, some other proof of concept functionality we didn't mention before is that because, proof of concept, the digital satellite TV provider gave users the possibility to rent movies from set-top boxes, to access customer service from set-top boxes, to access the biggest web auction portals in Poland from set-top boxes. And this, of course, required the credentials, user credentials. What we did, we implemented some kind of functionality which was able to sniff the HTTPS traffic and obtain the login credentials and dump it to arbitrary files. So at some point of time, this was also a risk for set-top box users to have some malicious code being installed on these devices. Okay, summary. Yeah, I'm good with time, so I'm happy. Vulnerabilities impact. So first of all, we didn't receive any response from ADB when it comes to the impact inquiry questions. So we don't actually know how many of the set-top box devices out there are vulnerable. So this information wasn't provided. We asked the company, but no answer to these questions. So we tried to do the estimation with respect to the publicly available data. So this is something retrieved from the Wikipedia and the ADB company website. So in 2010, the 16th million set-top box shipped, over 30 models. Some models designed under separate brand, customers from Europe, Middle East, Africa, Asia Pacific, Americas. But we don't know which actual customers beyond the one we verified in Poland actually had these vulnerable set-top boxes. So vendor's response when it comes to ONET, the web services provider, everything went smooth with them. So they confirmed and fixed all the issues in the web services, the arbitrary JavaScript injection issue of the web albums. Actually, we've noticed that the functionality related to viewing the photo sharing, photo albums on set-top boxes was removed from set-top boxes. So it's not available anymore, probably for security reasons. We don't know. Conax AS initially rejected both of our issues and later admitted to the issue regarding the push VOD, the one which allowed to see movies in December rented in November, regardless of the fact that December credentials were not allowing for that. And we received little detailed explanation that this was the result of running the affected service in a way specific to older generations of the Conax system. We don't know any more details regarding this issue. So probably well, I need to carefully choose my words. The last two companies, Advanced Digital Broadcast and ITI Now Vision, in February they released some statements, public press statements, in which they refer to our research as potential, as the source of potential insecurity, that the tests were conducted in a controlled environment, that no breach or abuse of the services happened, and everything was the word was spoken in that tone, yeah? And we didn't receive any response to the impact inquiry or status inquiry questions from January 2012. So what I can just say that I've been around 15 years, maybe too long, but this never happened. Usually there is some kind of a contact with the company, regardless of what kind of magnitude the bug is reported. I have experience of reporting bigger bugs and there are no problems with the vendors. So that's it. So final words. I think that the outcome of the project illustrates that there is some kind of a need for more thorough security evaluation of complex systems or the systems that are less known and the hardware platforms which are less known. So we found I think we found too many security issues. There shouldn't be so many of them, yeah, when it comes to this environment. So this shouldn't happen. What we also proved is that malware code is a threat for internet-connected digital satellite set-top boxes. So we showed that STB devices could be infected in the same way as PC users are infected these days when it comes to malware. So the question is, are smart TVs going to be next? Yeah. So this is the revolution we are experiencing right now, yeah? The smart TVs, and with all the rich functionality, access to many web applications. So, but they become internet connected, and at some point of time, you know, people should start thinking, yeah? These devices could pose some risk, yeah? I don't know if directly to the users, maybe when it comes to the stealing of user credentials, yeah? When it comes to accessing these services, but also when it comes to the access to the user's home networks, yeah, because these devices are deployed in users' home networks. So we think that set-top box manufacturers, when it comes to the conclusion from this project, so they are probably a little bit too much focused when it comes to the security of content and not quite ready when it comes to connecting the devices to the internet. And there is definitely the need for security in a digital satellite TV and smart TV ecosystem, because once we connect any device to the internet, we need to think about the potential impact about the security and privacy of users. So what I also think, and what I want to emphasize at the end, that potential legal barriers shouldn't discourage researchers from evaluating security of network-connected devices. Okay, that would be all. I am 1 minute past the, I apologize for that 1 minute above the, so
it's okay.
Thank you very much for, maybe there are some questions from the audience.
Yes, we could do a few questions.
But yeah, I'm ready to...
Anyone?
Yep. Yeah.
I know this is a bit of a non-technical, perhaps a little bit of political question, but do you see any signs of the TV industry finally gradually realizing that the DRM, the myth of DRM, is not really a realistic approach for managing their content? As an example,
that's a killer question.
One example, the music industry eventually figured it out, and they switched from DRM to watermarking.
Well, I'm not sure if I would like to go into that area, because it's sort of, you know, well, I personally don't like when I have, you know, that DRM protected music in iTunes. Yeah, I don't like that. So when it comes to the approach of the industry, I don't really think that's going to happen, and probably the reason for it is the providers of content, and probably, you know, the big providers, I mean the television networks, they dictate the rules. So, and this is probably the reason why, you know, all that stuff from the digital satellite TV provider up to the set-top box device needs to be protected by some means. So, but that's just my guess. And when it comes to the indication of a change of the approach, when it comes to DRM, I don't have any, yeah? So I actually need to admit that I've never been actually speaking with any representative from that industry about that topic. So it's really difficult for me to say something about it. Yeah, so I can just personally give my view and opinion.
Thank you.
Yeah, I was wondering how much of what you've been saying applies to digital terrestrial TV systems?
I don't hear you. Could you?
I was wondering if you could say how much of what you've been saying applies to digital terrestrial TV systems, as opposed to satellite-based?
I still didn't understand. Can I please maybe...
terrestrial digital TV, as opposed to...
Can I ask someone else maybe to repeat the question? I'm sorry.
I think what my neighbor means is, do you think the same issues apply for DVB-T and DVB-C? as opposed to satellite broadcasts?
Oh, you mean the terrestrial or the... Yeah, I know, okay. Well, you know, we haven't worked with the, you know, set-top box devices for terrestrial or cable, yeah? But you need to think from the following perspective. If you have these devices being connected to the internet, and I don't know if this is going to be, this is the direction that the operators are undertaking when it comes to the terrestrial and cable. So you still need to take into consideration that, you know, these devices could be put under attack. And there is definitely some kind of content and premium content which goes down the stream from the operator along the cable, yeah, along the terrestrial, which needs some kind of a security. So some issues could apply. I don't know whether this was what you were asking about, whether you were asking about the specific issues I mentioned, but I don't know this because I don't have information about the actual set-top boxes, the actual networks that were using the ADB set-top boxes. This information was not provided to us.
Okay, just one follow-up if you don't mind. I just wonder, are you releasing any tools?
No, we decided not to release the tools.
You showed you captured some MPEG streams on your computer, and all these streams were descrambled, or some of them were also scrambled.
I can't hear you well, and it's difficult for me to understand what you're asking about.
Okay. Okay, you hear me now?
Yeah.
Okay. So you captured some streams on your computer, and the MPEG streams were scrambled, or you captured only descrambled streams?
The MPG streams captured on the computer?
Yeah.
Yeah, okay. So we were doing the actual capturing on a set-top box by simply making use of the API, the kernel level drivers API, and we were simply dumping over the network the whole unencrypted packets to the PC, and on a PC we were simply, you know, adding those packets to the file. This is how this works.
Thanks.
Okay, so thank you very much. I invite you to the second part. Thank you.